Hey guys, Mr. Middleton here. Today we're going to talk about special right triangles. Starting our new unit. At the end of this video, you should be able to find the lengths in special right triangles, and you should be able to apply relationships in special right triangles. Okay, so let's look at our first special right triangles. We'll talk about two today: 45, 45, 90 triangles, and 30, 60, 90 triangles. First one, 45, 45, 90 triangles. What we're going to do is we're going to draw a right triangle that has a 45-degree angle. Okay. So I'm going to draw a triangle. It's not to scale, guys. Sorry, not natural at drawing 45-degree angles. Alright, so here we go. Tell it's a right triangle here because of our right angle marking, and we need a 45-degree angle, so I'm going to make this 45 degrees. Alright, now the question follows, what is the measure of the other acute angle? Okay, so not this one because it's a right angle. This other angle is going to be 45 degrees. Okay. Besides a right triangle, what type of triangle is this? Well, if this is 45 degrees and this is 45 degrees, we know that it is an isosceles triangle. Isosceles. Okay? And we know that because we know that if the base angles of a triangle are congruent, then its sides are congruent. And that's also called the converse of the isosceles triangle theorem. Okay, so just kind of a little bit of a review there, remembering that. So we can tell that this is an isosceles triangle. Okay, on your calculator, if you type in tangent 45, what do you get? Okay, so on our calculator, it's in degrees. I'm going to type in tangent 45. We get 1. Okay, now remember that the tangent of a ratio, or the tangent ratio of an angle, is opposite over adjacent. TOA, opposite over adjacent. Okay, and since both legs are, let's just say, I'm going to call it x. Since both legs are x, our ratio is x over x, which if we do this no matter what x stands for, this reduces to 1. X divided by x is 1, or anything divided by itself is 1. Okay, that's where we get our tangent ratio. Okay, so what we're going to do is we're going to use Pythagorean theorem to find the length of the hypotenuse. Okay, we can tell, first of all, that it has to be an isosceles triangle because 45, 45, 90, those base angles are the same. We're just going to keep x in as the side length so that we know that this is general, it applies to everything. And we're going to solve for h. We're going to figure out what h is. Okay, so using the Pythagorean theorem, if I want to find the hypotenuse, I'm going to say x squared plus x squared equals, let's just say, h squared, right? So 2x squared equals h squared. I'm going to take the square root of both of these. Okay, take the square root. All right, now this is kind of tricky for us a little bit in the sense that we have 2x squared. 2 doesn't really have isn't a perfect square. So I'm going to redo this left side a little bit. I'm going to write this up here so we can see how it's happening. Okay. All right, so I'm going to kind of separate these two things so we can see what's happening. We know that radical 2 times radical x squared is the same as radical 2x squared. Okay. Square root of x squared will give us x. Square root of 2, like we said, doesn't have a perfect square here. And so what we see now is that this hypotenuse is always going to be x radical 2. Okay, whatever this side length is times radical 2. So the length of the hypotenuse is radical 2 times the length of the leg. Okay, so our special right triangle up here, this 45, 45, 90 triangle, you need to kind of remember this this triangle because we'll be able to use this to find missing sides. We'll do that at the bottom here. Okay, so here at the bottom, we're given that AB is 8. This is a 45, 45, 90 triangle. Sometimes it's helpful to write all those angles in that you know. Okay? All right, we're given that this side is 8. So now BT, what will BT be? Well, since this is a 45, 45, 90 triangle, isosceles, then we can tell that BT will also be 8. No real math included there. Alright, and now we need to find AT. AT in this case is our hypotenuse. Our hypotenuse, like we said, is whatever this is times radical 2. So 8 times radical 2 will just be 8 radical 2. Alright? And so that's the simplest, really 45, 45, 90 triangle problem that we'll see. And there's really only two ways that we can see this problem, and here's the second way. Okay? In this triangle, notice that we're given the hypotenuse. Now this is always a little tricky for people because our hypotenuse is 10. Notice it doesn't have a radical 2 in it. Alright, so what I like to do for these problems is I kind of just make these x, this is x radical 2. Okay, now in order to find x, I need to kind of solve an equation that we have here. Okay, I know that this side is 10 and I know that this side is x radical 2. Okay, same side. So x radical 2 equals 10. I need to find out what x is so I can find the other two sides. What's stopping x from being by itself? Radical 2. What's radical 2 doing to x is multiplying. So in order to get rid of it, I have to divide by radical 2. So we have x equals 10 divided by radical 2. Which if we were just asked to give this as a decimal form, we could punch this into our calculator and figure this out now. But typically we'll be asked to write our answer in simplified radical form. Remember, that means that we don't want a radical in the denominator. So to get rid of the radical in the denominator, we will multiply by fancy 1. Okay, so not too long since we had to use that. We have 10 radical 2 over 2. And now we'll see, can we simplify? Remember our rules with radicals. We'll simplify outside by outside, inside by inside. And so 10 and 2 are outside. We can simplify those. That does simplify down to 5 over 1. So our answer then for x will equal 5 radical 2. And so BO will be 5 radical 2. BY will also be 5 radical 2. Okay, so these are typically the two 45, 45, 90 triangle problems that you'll see. Okay, you might be asked to recognize that an isosceles right triangle has to be a 45, 45, 90 triangle, but outside of that, these are the two problems that you'll see. Okay, so make sure you focus, pay attention to this, write this down, look at this, study this 45, 45, 90 triangle. It will be important to you. All right, flip it over to the back. Look at our 30, 60, 90 triangles. Like I said, we're going to look at two special right triangles, and this is the other special right triangle, our 30, 60, 90 right triangle. Okay, so let's follow along with the directions on the sheet and kind of talk through how we come up with the ratios for these sides. All right, so they're asking us in this triangle to label the shortest side S. So first of all, how can we tell what the shortest side is outside of just looking at it and saying, oh, this is obviously the shortest side? Well, this angle is 30 degrees, this angle is 90 degrees, and this angle is 60 degrees. Okay, so remember that our longest side is always going to be opposite of our longest angle. And kind of the same logic, our shortest side is going to be opposite the shortest angle. So our smallest angle is 30 degrees, and its side then would be here. Shortest side is S. Okay, we'll just call it S. All right. Now from there, we're going to prove our ratios. We're going to prove the ratios that I'm going to ask you to remember. All right. So if you follow along with me, what I want you to do is I want you to draw another triangle here, just kind of adding on to this one. Okay. Okay. Now in this triangle, I want you to make this 30 degrees. Okay, and if we make that 30 degrees, then we see that this will be 90 and this will be 60. Alright? So we can tell that these two triangles then that we just drew and the one that's already existing, these two triangles are going to be congruent triangles because of angle, side, angle. Okay? So now we're going to talk about the relationships between 30, 60, 90. So since we just showed that these two are congruent by angle, side, angle, then we can tell that by CP, CTC, corresponding parts of congruent triangles are congruent. We can tell that, I'm going to label this D, that DB is congruent to CB. Okay, DB is congruent to CB, right? If they're congruent triangles, then these two parts corresponding parts are congruent. All right? We can also tell that triangle ADC is equiangular. Equiangular. Okay, so we kind of started off by looking at these two triangles separate, but if this is 30 and this is 30, that makes this 60 degrees. This is 60 degrees, this is 60 degrees. They're all 60 degrees. Remember that every equiangular triangle has to also be equilateral. Okay, if it's equiangular, it's equilateral. It goes in the same thing that we were talking about labeling the short side and the long side. The shorter sides are across from the smallest angles. So if all the angles are the same, that means all the sides have to be the same. All right, so if this is equilateral, then we can say that all sides in triangle AB or ADC are going to be the same. All sides are congruent, in triangle ADC, okay? And so we can, if we know one of the sides, we know all the sides. And we do know one of the sides. We know that DC is 2S. That means all the sides are 2S. So DC equals 2S, and for our reasoning here, it's important that AC is 2S. So this is 2S. All right, cool. So what we're using this for, we're going to use this to say, okay, in a 30, 60, 90 triangle, we know that the side across from 30 degrees is S. The hypotenuse is always 2S. Okay, we're going to use this to find out the other side and kind of our conclusion. We're using Pythagorean theorem. We're going to use Pythagorean theorem to find out what that other side has to be. So we can find that other side, remember, because we can say that, I'm just going to call this, let's just call it H. Sure, why not? Okay, I'm going to say that S squared plus, I like X. X shows it more as a variable, okay? S squared plus X squared equals 2S squared, okay? All right. So, 2S squared, okay, because that's what we're doing, we're squaring that whole side. So, as we simplify this, S squared plus X squared equals 4S squared, because 2 times 2 is 4, S times S is S squared. And then as we go about it even further, subtracting S squared from both sides, we end up with, sorry guys, ran out of space, X squared equals 3S squared. Again, we're going to take the square root to find out what x is. Same logic that we use with our 45, 45, 90 triangles, we can come up with s radical 3. So this height is s radical 3. So I'm redrawing this 30, 60, 90 triangle so we can look at it in its final form, how we want to remember it. Across from the 30-degree angle, we have s. Our hypotenuse will be 2s. And across from the 60-degree angle will be s radical 3. All right, so the length of the hypotenuse is going to be 2 times the length of the short side. The length of the longer side is going to be radical 3 times the length of the short side. So it's important here, you see that the short side is important to find. And usually if we're given any other side, what we'll do first is we'll find the short side, because everything else that we know can be found using the short side. All right, so let's look at this, these possible situations. Okay, you can be given the short side, like this problem here. We're given the short side, we know because it's across from the 30-degree angle, and find the other two sides. Okay, again, you'll have to remember this triangle so that you can use this quickly. Makes it a little bit faster than using trig. Okay, so I'm given the short side, then I can say, okay, if the short side is s, so s, I like to just go through and label these sides sometimes because it makes it a little bit easier for me to see what I'm doing. So s is 5. B is s times radical 3, so 5 times radical 3. C is 2s, so 2 times 5, which is 10. Pretty quick. I can be given the long side, okay, or the longer side. Here I'm given 60-degree angle, and that this is 12. And like I said before, I like to label what these ratios are so that it's easy for me to set up an equation if necessary. So here we go. Here's our equation that we have. 12 equals s radical 3. I can find out what s is by dividing by radical 3. And then again, you see that we're probably going to have to use fancy 1 because we have a radical in the denominator. And when we do that, we have 12 radical 3 over 3. And we can simplify that. 12 and 3 simplify to give us 4 radical 3. So I know that s is 4 radical 3. I'm going to use that. That means that this side's 4 radical 3, and this side's 2 times 4 radical 3, which is 8 radical 3. Okay? So now x is 4 radical 3, y is 8 radical 3. And we also will be able to solve it if we're given the hypotenuse. Okay, and our hypotenuse is a little bit easier than having the short side because we know that our hypotenuse is 2s. Okay, so this is s radical 3. 2s is 16. 2s is 16. Then I can find s by dividing by 2. S will equal 8. Okay, and this side will be 8 times radical 3. 8 times radical 3. Alright, so 30, 60, 90 triangles, 45, 45, 90 triangles. Make sure you spend some time looking at these triangles and committing those to memory so they're easier and quicker for you to use. See ya.